half of this today. We're going to finish the rest of it on Tuesday, and that's going to conclude the material that's going to be on the upcoming exam. So you should be able to do most of your homework after today's lecture. And so the first day that the test will in the testing center will be next Thursday, okay? So you still have a weekend to get caught up. You really should get the prior chapters under control first. In other words, know about how to do all of your stuff with your equations about ionic, net ionic, and molecular equations, identifying if something is a redox reaction, oxidation reduction, and then the stuff that we covered on gas laws, and the stuff that we just covered on thermochemistry. So you do have a lot of concepts to kind of review, all right? So this would be a good time to try to start getting that under control for next week. We will go over the practice exam next Thursday in class. That's an optional lecture, so if you want to go take the test during that time, you're more than welcome to do so. I will put an answer key up. There is an answer key up on Blackboard, so you can go and look at that and check your work. But we will work through that exam together in class next Thursday also. And if you have any questions, you can bring those to me as well. Okay? Any questions before we get started on this? Okay, now I will preface this by saying you all have to have a little bit of faith in me while we go through this stuff. There will be some concepts that are kind of fuzzy, but I will promise that I will tie them all together nicely. Okay, so you'll see where this is all going at the end. There is some pretty high-powered physics in the next few slides, so don't let that intimidate you. Just recognize that the critical question still remains about the location of an electron and how we can describe that electron, which is ultimately where we're going with this whole discussion. Now, I think last time we talked about the relationship between frequency, wavelength, and energy, okay? So we said that you could differentiate energy based on the wavelength of a particular type of light that's given off. And that leads me into a discussion now about color, okay? So as you look, you probably suspect the color that you see in the color spectrum is divvied up based on wavelength, okay? And then therefore it is based on energies as well. Everybody should know what the color spectrum is, the Roy G. Biv, okay? So red, orange, yellow, green, and then blue, and then indigo they don't have in here, but then violet, and I think they added that for that acronym. But basically what that's saying is that wavelength always, when you see a rainbow, those colors always appear in that order consistently. And that's because light is being broken down from a low energy all the way to a high energy spectrum. Red wavelengths tend to be large, so have lower energy, and violets tend to have small wavelengths and have higher energies associated with them. And just because it is not a color that we can see, does that mean that that is not also a type of wave? I mean, can you have wavelengths that are not visible? That's what I'm getting at.
Yeah.
And a good example of that is your microwave oven. Okay, it doesn't glow. Okay, when you turn it on, well, other than the bulb that's in there. Okay, but you can't see the microwave radiation, but it's going on in there. Okay. Likewise, when you're outside, okay, and you get a sunburn, right, you can't see the ultraviolet light that's damaging your skin. Okay, because it's also not colored. So there are waves that we can't perceive as well that are not colored waves. Now here's again an illustration of what we're talking about. Red wavelengths are larger, yellows kind of medium, blues and violets tend to be smaller. Smaller wavelength equals higher frequency equals greater energy. So is that, all that still makes sense? Waves can also have different amplitudes which affect the brightness and the energy of those waves as well. So if you have a very high amplitude, that's a very intense light versus a low amplitude, which would be a very dim light, okay? And so if we were to look at the full electromagnetic spectrum, you will see that the color spectrum is a very tiny sliver of what we actually think is out there and have measured. Ultraviolet, of course, being on the other side of violet, being higher in energy, and then X-rays and gamma rays, which all have very, very small wavelengths and very high energies. And these are all things that can be produced by the sun, so why are we not all dead? Anybody know this? Well, that filters out UV, but not this other crazy business over here.
Sounds great.
So let me ask you a question about all of this. So now, have you everybody familiar with SpaceX, that company? Or the guy who owns Tesla and all that, and he wants to do this space exploration, right? He's gonna put a Tesla in space and all that business. Okay, well, he's wanting to make this into a tourist industry, send people up into space, right? So what about having a city on the moon? We could get stuff up the moon, resources, water, atmosphere, all that business. If we could have a little pod up there like we have a space station, surely Moon City is more sexy than the space station. Does everybody agree with that? I mean, if you could go up and get some moon rocks and come home in the weekend and show your friends about, look, there's moon rocks I got off the moon, that is certainly better than just saying, I just rolled around the space station. So if I'm thinking about making money, I'm thinking I want to send people to the moon and come back. Well, why is that not a good idea?
Radiation?
Well, what about the space station? I mean, isn't it up in space? They live up there for almost a year sometimes.
They're exposed directly.
How? See what I'm asking? I'm thinking Moon City is more profitable than space station. So why hasn't happened yet? Time? Like, what do you mean? Like, just take too long to get there? No.
It's too expensive.
Just think you can do it. You could do it. Hey, I mean, we're talking rich people here. I mean, their people pay a lot of money to do crazy stuff. Like, why is it okay to be up in the space station, right, for almost a year? Why could you not be on the moon for the same length of time? That's all I'm asking. Let's say if you get money's not a problem, we can build Moon City, all that business. Why is that not feasible? Where's the space station? Here's the Earth, right? Here's space station. Here's the moon over here, okay? So why is a space station safe compared to the moon? The Earth. What's the Earth got? Well, we don't usually think about it, but it's got this molten metal core, and it rotates, right? And when it does that, it creates a magnetic field that goes around it. So the space station is actually inside the magnetosphere of the Earth. That's the aurora borealis that you see, okay? That's all the radiation that's being filtered out from the sun that would kill everything on the planet, okay? So if the Earth's core wasn't molten metal and rotated, we'd all die. The moon doesn't have molten metal core, and things aren't looking good up there on the moon, right? You'll agree with that? It's not looking good. Okay, there's not only no atmosphere and no water, but it's looking like life is not really feasible up there at all, okay? And that's why you don't have that magnetosphere to protect it.
So they want to go to Mars. Does Mars have a...
Yeah, see, Mars does have a molten metal core and rotates. So Mars, even though it's further away, is more feasible for sustaining life, okay? So anyway, those are a lot of trivia questions you can get right now on Trivial Pursuit and Final Jeopardy and that kind of stuff, okay? Does that make sense? Okay, so these radiations are all really tied to, our life. And is everybody familiar with infrared radiation? Infrared radiation being like the radiation of heat, okay? Also not something visible, but is definitely there, okay? And technically has lower energy than the red color because the wavelengths are larger and larger waves like radio waves and TV waves. I've heard for a while that cell phone radiation was going to kill people, but that's kind of bogus because cell phone radiation is so minuscule compared to, say, these other things. It is far more dangerous to go get an X-ray. okay? Have we talked about that?
Yeah.
Like you have to put the iron thing, you have to put this like lead suit on, and then the X-ray technician is gone when they zap you. Okay, that's because that's dangerous radiation that you're being hit with. Okay, so how this all ties together with electrons is that since those waves have different energies associated with them, and so we know that elements burn different colors, those are kind of like fingerprint signatures for that element, like the energy that it's giving off. And that energy that it's giving off has a lot to do with the distances that the electrons are traveling within an atom itself. In other words, they're not just kind of locked into one place, they kind of move around the atom, okay? And that moving around is what causes the generation of those waves. Obviously, high energy radiation, like the stuff we were talking about ago, like the stuff that you'd experience on the moon, that will kill you because it's high energy radiation, passes through your body, will damage your DNA, and that probably means cancer and that kind of stuff down the road. One of the things that fell out of all of this, and something that was, I guess, a big problem in the early 1900s that nobody had a really good answer for, was this experiment that was set up that was called the photoelectric effect. And that is, when you shine a bright light on a metal, it turns out that the metal actually begins to eject electrons off of its surface, and you can detect those electrons. And so what everybody was thinking is that, okay, so if you shine a light on the metal surface, if you shine it on there long enough, that eventually the electrons will pop off and you'll be able to detect them. Like the electrons will start to store the energy and then they'll pop off. And if you were to use, let's say, a really bright light versus a dim light, well, that the bright light would cause more ejections than the dim light because the bright light would have more energy. And that's what everybody thought would happen. And in fact, that wasn't what happened, okay? It turns out that it didn't really matter how bright or how dim the light was. What mattered was that the light had the right wavelength of energy. In other words, if the wavelength was too big, okay, overall, and the light didn't have enough energy, it wouldn't eject electrons, and it didn't matter if you shine that light on there all day and all night. There would be no electrons come off. So the electrons didn't store energy. So everybody was like, well, why are the electrons waiting for this special type of wavelength to come along for them to absorb? I mean, why aren't they just storing the energy and then ejecting off the surface over time? And the reason is because it turns out that there was actually this thing called the threshold frequency. That is, there was a point at which electrons would not eject regardless of how long or how bright the light was that shined on there. So that was a real problem, and the person who actually explained it was Einstein. This is what he really won his first Nobel Prize for, was for understanding how this happened. Einstein began to think that electrons didn't really behave like other types of things in nature. Like they didn't store energy. It was like electrons would actually absorb packets of energy and then would come off all at once, okay? In other words, they had to be in tune with what the wavelength was. Like, have you ever heard, like, well, we're just not on the same wavelength? It goes doubly true for electrons. If you don't have the right wavelength for the electron to absorb energy, it just won't absorb it, okay? It ignores it. So you have to have the right wavelength of energy in order for an electron to be emitted. And that's because Einstein believed that electrons and atoms themselves absorbed energy in terms of what are called quanta and emitted things that were called photons of light. In other words, very specific wavelengths of light were being emitted by atoms. And that would explain why when you burn elements, they'd only produce a certain color, is because their electrons were only in certain locations to produce those colors, okay? So this kind of made sense. Mathematically, you could actually calculate the energy associated with this by understanding the frequency of that particular light and knowing a constant. And that constant is what is called Planck's constant and is given the symbol H. Now, just like all constants in this class, you do not need to memorize these, okay? I'll provide them for you on an exam. But you do need to know how to calculate these energies using this equation, okay? Now, this equation can be written in two forms. E is equal to Planck's constant times the frequency, which is the same thing as saying it's Planck's constant times the speed of light divided by the wavelength. And so I'll ask you to remember the equation that we went over last time, which was wavelength times frequency is equal to the speed of light. So if you just solve for frequency, it's c divided by lambda, which is where that third equation is coming from on that slide, okay? But this tells you something that we already predicted. That is, as frequency goes up, energy goes up. I'll remind you of my analogy of that. Does this versus this, which one of those two have more energy? The second one. Which one has a higher frequency? The second one. So higher frequency, higher energy. That's what this is saying too. So as the frequency would go up here, so too would the energy. Does that make sense? Now you need to pay attention to the units here, so you can see this is joule seconds, okay, is what the Planck's constant is. And frequency is measured in inverse seconds. So inverse seconds times joule seconds is going to give you joules, which is an energy unit that we've been using in this class, okay? So if we want to calculate that, okay, all we would need to do is to know something about the wavelength and something about the energy, okay? So for this particular question, you are told to calculate the number of photons that are in a laser pulse that has a wavelength of 337 nanometers and has a total energy of 3.83 millijoules. So that's what the little m stands for, so millijoules, okay? Now this is how we're going to do this problem. We're going to calculate the amount of energy that's in one photon, okay, first. That's where the E is equal to H times C divided by lambda comes in. That will give me the energy in one photon. If we know the energy for all the photons, well then we just take the total energy, divide it by the energy for one photon, and that'll give me the energy of all the photons, the number of photons that are present, okay? So we're going to solve for the energy of one photon and divide that into the energy of all the photons present to get the number. So here's what you do. First, you got to know what these symbols are. Okay, so again, nano, remember that? What's that? 10 to the negative 9. Okay, so that's how you would convert between nanometers and meters. And then we have millijoules, and milli is times 10 to the negative 3. Okay? So now, to do this, what we're going to do is we're going to take our nanometers, we're going to convert it to meters. Once we know that, we'll get the energy in one photon, then we'll divide that into the total energy to get the number of photons altogether. Okay? So these are the things that you're going to need to know. So we need to know the equation between energy and wavelength. We need to know what a nano is. We need to know what a milli is. And we need to know that this is going to be the logic here we're going to use. The total energy of the whole pulse divided by the energy in one photon to get the number of photons. Okay? So those are the conversions that we're going to need to do the math. And here's how you plug the numbers in. So this right now will convert our nanometers into meters. So we'll just multiply that by 10 to the minus 9th to get meters. The reason why we want to do that is you need to use that number in the second equation. So the energy of one photon is equal to Planck's constant times the speed of light divided by the wavelength. Planck's constant is here, okay? That's in joule seconds. Speed of light is here, that's in meters per second. And then you have the wavelength here, which is in meters, okay? And if we did everything right, everything should cancel except for joules. So seconds cancel, and meters cancel, and we'll be left with joules. So that's the amount of energy that's in one photon, okay, of this particular energy, all right? Now to get the total number of photons present, you're going to need to take this number, which was in millijoules, that's the energy in all, okay, of all the photons combined. and convert it into joules so that these two units match up, joules and joules, okay? Then you just take the larger number, this one, and divide it by the smaller number. Does everybody see that? That 10 to the minus 3 is larger than 10 to the minus 19.
Where did the 10 to the minus 3 come from on the numerator?
That is convert milli into joules. In other words, there's
Oh,
a
okay.
thousand,
Yeah.
there's 1,000 millis in something. So this is just,
threw me off.
yeah, it's just switching it around. So you could have done the same thing and put the 1,000 in the bottom and 1 on the top. You'd still get the same result, okay? So now you know that, you take the energy in your total pulse, divide it by the energy in one photon, and then that will tell you the total number of photons in the pulse, okay? This math, the reason why you want to be able to do this kind of stuff is because you're going to see all of these units used, all these constants are going to be used in this discussion, okay? And we're going to be talking about waves as if they have a specific amount of energy, and they do, okay? And the connection is this equation, all right? Now that being said, all right, all this is really telling us is that, well, electrons don't behave like other types of matter, okay? They don't continuously absorb energy. They are selective about the type of energy that they absorb. The reason is because electrons themselves behave like waves, okay? Just like energy. So there's a relationship between those two things. So where this becomes useful is if you were to look at, say, the atomic spectrum of an element. That is the light that is given off by a particular element when we burn it. And we have done this when we have looked at flame tests. One of the things you will know about these patterns is that they are not continuous. They only show discrete lines, okay? In other words, if you were to look at the energy that's given off by the lights in this room, which are mercury lights, and you looked and viewed them through a prism, you would only see 4 or 5 colors, okay? Now my question is, why are you only going to see 4 or 5 colors? Why aren't you seeing a full rainbow?
Because
Does it have
there's a
to do with, like,
spectrum.
absorption, like, or what it reflects off? Because like colors are what, like the color you see is what is giving off all the colors that it's not.
Well, let me ask you this question. Where is just a color coming from?
Light.
Yeah, but where's it, how is it producing it? Okay?
Like so. It's,
So let's think about it like
The
this.
absence of
So
the
if you have an electron, right, going around a nucleus, okay? And let's say there's another place that electron can go, all right, some distance away from that. If we're gonna hit this with some energy, okay, like electricity or something, that electron can move up to that next energy level, right? So now it's over here. This is what's called the excited state, meaning it's got energy now, it's got more energy. But it doesn't stay there. And it actually moves back to its ground state. Now my question is where did that energy go? Because energy is conserved. So if it moves back over here, where did that energy go? It goes off as light, okay? So basically what you're looking at, the light that's being produced by these bulbs, is basically the way that the elements are releasing that energy. That's why we're seeing the colors that we're seeing, is it has to do with the distances between these regions, okay? And again, what do you think would happen? The greater the distance, the higher the energy, the
more
smaller
light.
the wavelength, right?
Yeah.
So that explains where the colors are coming from and why there are different colors. Now, let me just throw this out here also, and you'll see this in a minute. There's a guy who actually calculated how you could predict the distances between those regions, okay, in an atom. This guy, Rydberg, he was not a chemist, he was a mathematician. And so he actually looked at a hydrogen atom and came up with this equation to explain this spectrum right here, okay? So this is, let me show it to you without the lights on, because this is kind of hard to see. What you have here is a hydrogen gas is being irradiated, just like we were radiating these mercury bulbs, except now the hydrogen light is being passed through a prism, and there are 4 colors that come out of it, okay? And so there are 4 colors here. Now, do you guys remember about the colors? Like, does red have more or less energy than purple? Red has less energy than purple. So that means its wavelength is bigger, okay? And so purple has a smaller wavelength.
And higher energy.
And higher energy. Now here's my question. How many electrons does a hydrogen atom have? 1. Okay, H2 has 2, but let's say one hydrogen atom has 1 electron. Well, why is there not just 1 line? Well, nobody said that there just had to be one place that electron could go.
Okay.
So there may be just 1 electron, but could it not go to different regions? Yeah, okay. Do you think the regions are equally spaced based on looking at that spectrum? No. Okay. So not only is this proving to us that there's more than one area that the electron can go in an atom, it's telling us that those are not equally spaced, okay? And here's another thing. What about all the stuff in between? It just doesn't go there, all right? And this is really a big fundamental difference about how we think of classical physics and non-classical physics. I mean, if I take this marker and I take it and I throw it across the room like that, everybody can follow that with their eyes from the moment it left my hand until it hit the floor. That's classical physics. And you can make an infinite number of measurements from the moment it left my hand to the moment it hit that floor. Like, where was it after it left my hand after 1 second? Where was it after 1.1 seconds? Where was it after 1.111 seconds? We could do that forever, right? But what if I told you that in this atom, the marker exists in 2 places, in my hand and over there on the floor, and nowhere in between? Are you getting that? So you're like, well, how the hell did it get over there in the first place? It just appeared over there. It's like it absorbed energy and was over there, okay? And you can't follow this trajectory. That's what this is saying, because if it did that, you should be able to see the light all along the way that it travels all the way down to the floor. It could give off, potentially, a whole bunch of different, maybe like, well, I'll go this far and I'll go back. Well, I'll go this far and I'll go back. Well, I'll go this far and I'll go back. Like, why is it waiting until it gets all the way over there before it comes back over here? Does everybody see what I'm saying?
I'm kind of lost. I just don't understand, how can you not, how do you know that
teleport?
came from that if it can't be measured?
Well, see, you can only show the final and the initial because of the wavelength that's given off.
Is it also have to do with the refraction of light?
Well, it has to do with the fact that why is there nothing in between these spaces?
Yeah.
Why are there these big gaps here?
Oh, okay.
That's what I'm asking. Why does hydrogen always give off those 4 colors and nothing else? Regardless of how much energy you zap that
And
with.
this may or may not be related, but I remember learning a long time ago about the colors that give off. So the color green is the color green because it's reflecting all
Yes.
the colors
Yes.
that it's not.
Yes.
So it's actually everything but
Yes.
green.
See, plants appear green because that's the color they're not absorbing.
They're reflecting.
Yeah. Plants absorb red light and blue light.
Yeah.
That's what they need. Okay?
Is that related to this at all?
Very much so. Okay? Because you can look at it in terms of an emission, that's what's given off, or you could look at what's called an absorption.
Yeah, that's
In
what
other
I was
words,
thinking,
that's the
absorption.
reverse of this.
Yeah.
So it is very much related
Okay.
to that. Okay? So the colors that we perceive are actually the colors that are being reflected. Okay? not absorbed, okay? So that's one of the things you think about, because chlorophyll actually appears to be green in plants because that's the color it's not
Right.
absorbing. It needs red light and it needs blue light specifically to make the plant grow, okay? So I don't know if you knew that or not, but that's a good point. It very much is a part of this discussion. What I'm trying to get across, though, is that this is a different set of rules, okay, than what normal matter follows, okay? Like when you get down to the level of an electron, it's like electrons have their own rules that they follow, okay? Like they can be in some places and they can't be in other places, okay? And that's going to be very important in this discussion. You will also notice that when we look at spectrums of elements, they can get more complicated. And why do you think that would be the case? More electrons. So you start to get more complicated spectrums as you throw more electrons into the mix. And different colored lights, because those electrons are in different locations, okay, than different elements, okay? So again, we're back to that again, is the spacing between those different regions that electrons can travel. And this is what I was talking about, is when you look at an atomic spectrum, you can either look at the energy that's being given off or the energy that's being absorbed, okay? So the reverse of that, okay? So it can be viewed as emission or absorptions. And we're going to do an experiment about like this in a couple of weeks when we look at some absorption experiments that we do in the photospectrometers. Okay, now all of this was basically leading to an idea of trying to predict a map as to where these electrons would be. One of the first people that tried to tackle this was Niels Bohr. And Niels Bohr latched onto this idea that Einstein had about electrons existing in specific quantized regions. In other words, that it appeared that atoms only choose to absorb certain types of energy. Well, what if that is because the electrons are spaced out in a particular way around an atom? Now, I don't want you to think that this is a mystical concept, because it's not. There are all kinds of quantized values that are present, and a lot of them are artificial. For instance, could you go to the HEB and buy 2.5 cups of milk? Like if you went and you asked the managers, like, yeah, I want 2.5 cups of milk. And they're like, okay, sir, you can buy a cup, a pint, a quart, half gallon, or gallon. Like, but that's not what my recipe calls for. Like, do we need to call security? I mean, so what do you have to do? You have to buy more than you need, right? And pour it out yourself. Whenever you have specific values that you have to go with, those are quantized values, okay? Meaning milk is only sold at the HEB in those 5 quantities, and that's it. That's a quantized value, okay? Now, can you pour out whatever you want? Yeah, that's a continuous model. Okay, so you can have both of these in nature. Like if you have the stairs, right, that you go up, okay, you can be on step 1, step 2, step 3, step 4. Could you be on step 2.6? No, you're either on the step 2 or you're on step 3. Do you see what I'm saying? So as you transition, but then you don't think about that. You're like, okay, well, I'm on step 1, now I'm on step 2, now I'm on step 3, etc. You're not thinking of any of the transitions in between. You're just thinking about, are you on step 1, are you on step 2, or are you on step 3? But if we got rid and pulled out all the staircases in the building and we just built ramps that you've got to go up, well, could you be anywhere on this ramp? Yeah, an infinite number of ways. You could be here, you could be here, you could be here in the middle, you could be all the way up here. So there it's not quantized, okay? What I'm getting at is electrons follow the model like the staircase, okay? Where they can be in certain places, but they can't exist in the in-betweens, okay? It's heavy, right? Okay, but that's what this is saying. And that's what Bohr was getting at with his model also, is he wanted a way to represent that and actually try to show where those electrons would be located. Now, just like what I was saying a moment ago, electrons travel in orbit some fixed distance from the nucleus, something that he called the stationary states, okay? And that would be proportional to however far that electron was from the nucleus, okay? In other words, the further the electron was from the nucleus, the more energy it would have. And the closer it was to the nucleus, the less energy it would have. And in order to jump further away from the nucleus, you would need to absorb energy. That's going to be an endothermic process, okay? And if you go back towards the nucleus, well, that's going to be an exothermic process. It's going to release energy, okay? Now, something I didn't mention before, but I just thought about right now, which is if there are more than one places that this electron can go to, what if it absorbed a whole lot of energy all at once and it went all the way out here to the one on the far end? What do you think could happen when it starts to go back to the ground state?
Could you get stuck in another one?
Well, it could go all the way back down all at once, but it could also do what?
Take steps.
Yeah, it could go back and cascade back. So all of those would be wavelengths of light that you would see. Again, another reason why there's more than one color, okay, that you would see in an atomic spectrum. And then you have to ask yourself, well, are there going to be things that we can't see?
Yeah.
Are there energies that are not visible? And you say, yes. Can you see ultraviolet? No. Can you see infrared? No. But those are energies that could be produced by an atom. So that's another thing we have to consider is it's not just the visible spectrum as well, but also the things that are not visible, okay, that are present too. So here's an equation I'd like us to think about. So there are three formulas that I want to bring to bear that we've talked about so far. And this is going to be kind of the big equation for bringing all this together. One of them is this one. Lambda times nu is equal to C. One of them is this one. Energy is equal to H times nu. And one of them is the equation that we talked about in passing, this guy right here on the bottom. Okay. Now, this equation right here, this number, this is just a constant, okay? This 1.07, 1.097 times 10 to the 7. This is what is called the Rydberg constant, so it's written out like this, R sub h. And this is 1 over n1 squared minus 1 over n2 squared. Okay, now this is what I want to do. I want to take those three equations and I want to combine them.
I have a question. What was that thing that you just wrote up at the very top? Like, what is that?
That's
Lambda?
this,
Yeah,
this here,
so is it lambda times that?
yeah.
Okay, I didn't know if it was like.
No, it's lambda times, it's wavelength times frequency is equal to the speed of light.
But I didn't know if it was just like.
No, it's the same thing as this, I just rewrote that. Okay? Okay, now this is what I want to do. I want to get an equation where I have energy on this side, and on the other side, I want to have these n values. Now, I haven't said this yet, but those n values have to be whole numbers, like 1, 2, 3, 4, 5, something like that, in order for the math to work out. What do you think those numbers correspond to?
Wavelength.
The regions that an electron can exist in, okay? Like 1, 2, 3, 4, 5, etc. Okay? So what Bohr wanted to do is to get an equation in terms of energy that it showed the distances between these orbitals, okay, or these regions that electrons could exist in. So I'm going to take this equation right here, and I want to solve for frequency, okay? And I want to put this in terms of wavelength. So if I take this equation right here, this lambda times nu is equal to c, and I solve for frequency, that's just going to be c divided by lambda, okay? Now I'm going to take that value, and I'm going to plug it into that equation that I've put a box in over there. So that's going to be E is equal to h times c divided by lambda. Everybody okay with that? Now I'm going to rewrite that out, and I'm going to say, okay, that's h times c times 1 over lambda. Everybody okay with that? Okay. Now I'm going to take that, I'm going to plug in this equation right here. H times c times r sub h times 1 over n1 squared minus 1 over n2 squared. Okay? Now if you multiply all three of these numbers together, okay? If you take h, if you multiply it by c, and you multiply it by r sub h, you get what's called the Bohr constant. Okay? Now there's no reason to memorize it because it's just those three numbers multiplied together. Okay? Now what does this tell you? Well, what it tells you is if you know where your electron stops and where it starts in terms of 1, 2, 3, 4 on that side, you can plug those numbers in here and multiply it by that constant, and that will tell you what the energy is that's going to be released, the energy of that photon, okay? And we already know that there's a relationship between energy, frequency, and wavelength. In other words, the greater the energy, the greater the frequency, and the lower the wavelength. Okay, you guys remember that relationship? Smaller waves have greater frequency, have greater energy. Okay? That would be if you were traveling between, let's say, distances that are closer to the nucleus. Okay? Like the distance between 1 and 2 versus 2 and 3. We don't need to actually solve this to prove it to ourselves. So if you're looking at 1 over 1 squared minus 1 over 2 squared, like the two closest, right? Number 1 and number 2. What is that difference?
3/4.
Yeah, that's 1 minus 1/4, which is 3/4. Okay? Now what if you plugged in the next two numbers? Like 1 over 2 squared minus 1 over 3 squared. That's 1/4 minus 1/9. Okay? Whatever that is. Okay? But is 1/4 minus 1/9 anywhere close to 3/4?
No.
Does everybody see that 3/4 is much larger compared to that? What's that telling you?
Like the distance is greater between and then it gets smaller as you keep going on.
Yeah, it's telling me that the energy that's transitioning between 1 and 2 is much greater than the distance between 2 and 3. What do you think would happen about 3 and 4?
It'd be even smaller.
Okay, so I could take this now and I could actually draw a much better picture knowing this. Okay, so in other words, if this is the very first shell, this one is 1 here, and I could say, okay, well the distance between 1 and 2 is going to be the greatest distance, okay, between those two. Well then that means that if I was going to look between where 2 and 3 is, so this is the distance here versus the distance here. Well what about 3 and 4?
Smaller.
Yeah, even closer together. So they get closer and closer together as you go further out via what this equation is telling you, okay? So it's not only that they're not equally spaced, it's that they're getting closer and closer together as you go further and further out, okay? And what do you think is happening to the energies between these?
They're getting smaller.
They're getting smaller.
So what happens to their wavelengths?
It gets longer.
They get larger. Okay, so here's a rule of thumb that's worth knowing, okay? So if you're looking at a photon, okay, and that photon is transitioning from, let's say, any shell, any value of n, down to the very first energy level. So that means 2 to 1, 3 to 1, 4 to 1, all of those to the first energy level. That is all going to be UV radiation, okay, that's going to be observed.
And the shell is an orbital?
Yeah, like a shell, yeah, think about it like that for right now. I'll give better definitions in a minute, okay? Bohr used the word shell, okay? Orbital came later, okay? But we'll say those regions, okay? Now, it turns out that if n is equal to any other value, any shell, n, and if you go to the second energy level, okay? So that means 3 to 2, 4 to 2, 5 to 2, 6 to 2, all of those. That's colored light. That's light you would actually see.
That's probably a fun question. I guess I'm confused because, like, I thought every electron was set, like, into a certain orbital, and then there's the ground state of the electron, and then they get excited, so they move to a different orbital. Does it not change what the element is because it goes back to the ground state when it goes off?
We're only talking about hydrogen here.
Oh, yeah, but that's what I'm like saying. So like if it, I guess the electrons is the same number of electrons, it doesn't change, but they can still bounce back and forth.
If it's not hydrogen, this model breaks down. So this is only for hydrogen, okay? Having one electron and one proton.
Okay.
And we're going to get to what you're talking about in just a minute, okay?
Wrap around the
Yeah, for right now, I'm just telling you, this is what you'd see for a hydrogen atom, okay? Now, anything else, all other transitions, that means we're talking 5 to 3, 7 to 4, 6 to 3, whatever. Those are all going to be IR, okay, energies, okay? Those are going to be, wavelengths are going to be much larger because the distances are going to be much closer together between those shells, okay? So these are the three types of colors that you see that are the three types of energies that you see that are given off by a hydrogen atom via that equation, okay? So what do you have to be able to do with all this? Okay, how would you get a question about this? Well, there could be two aspects of this question. One is, can you do the math, plug in the numbers, and solve, okay, for the energy using that equation? And could you take a model like this and tell me what's going on? Like, is energy being given off? Is it being taken in? And could you compare the, like, let's say, which wavelengths are bigger and which wavelengths are smaller? Which frequencies are bigger, which frequencies are smaller? Which energies are bigger, which energies are smaller? And could you identify those energies in terms of UV, color, or IR? Okay? We're going to solve the first aspect, the math. We'll do that one together. Then we'll do a conceptual one together with a Bohr atom. Okay? Okay, so this says everything that we just stated, okay? Basically, the larger the value in, the closer the two orbitals get together. N is a number that can be any integer, any whole number that's greater than or equal to 1, and what it represents is a region that you find electrons some distance from the nucleus. If you were to travel out all the way to infinity, Like if you went from infinity, from the nucleus out, that would mean that's an electron that is 1 divided by infinity squared, so that would be 0. So there would be no energy associated with that electron anymore because it will have escaped from the atom. In other words, it will have been knocked off from the atom. The larger the value of n, the larger the orbitals. N as n gets larger, the amount of energy between the orbitals gets smaller. This number right here, does anybody know where that number comes from? That's H times C times the Rydberg constant. That's those three numbers multiplied together.
So that's the Bohr's.
Yeah, so then it's like, oh, wow, this is the Bohr constant,
Okay.
but it's really those three constants multiplied. Okay. Okay. So if you were to graph this out, okay, and you were to actually calculate those values, okay, for n is equal to 1, 2, 3, and 4, these would be the numbers that you would come up with. Notice all the numbers are negative also. This is writing it as if that's energy released. In other words, the electron travels down to that energy level, okay?
So it's
Going from here to here, or from here to here, from there to there, etc., okay? But notice that the distances between 1 and 2 are much bigger than the distances between 3 and 4 and 2 and 3. So 2 and 3 is, much smaller than the distance between 1 and 2, and that's because of what we just proved mathematically. 1 minus 1/4 is a lot bigger than 1/4 minus 1/9, okay? And that's where those numbers are coming from. Now, what's going on is something that we've already said, is that the electron is absorbing some energy, transitioning to this higher energy level, and then when it relaxes down to a lower energy level, it gives off a color of light, okay, or a type of light. And that light can be either, for a hydrogen atom, UV, IR, or visible, okay, one of those three. So what type of light would be given off in this transition here, where it's going from 3 to 2?
Color?
It would be a colored light, okay, that would be given off. And in fact, the type of color that's given off depends on the transition. Like if you transition from 5 to 2 versus 4 to 2 versus 3 to 2, notice the colors of the arrows change here, okay? So a transition between 3 to 2 is going to be a lower energy transition than, say, 5 to 2, right? And so you see that if you did the math, you'll find out that the wavelength is about 656 for red versus 434 for purple, okay? And so shorter wavelength, greater energy, okay? And again, purple light has more energy than red light does, going back to that. All right, does that make sense? And then all of these transitions down here are not visible. Why not? All the way down to the first energy level. UV radiation is given off there. So any transition to the first energy level is going to be a UV radiation.
Why is it less energy? I thought like the further it was going, the more energy is being put in. Like, why is it less?
For which thing again?
Like your last example you were said.
See, they're all ending up at 2. But you're going here 3 to 2, 4 to 2, 5 to 2.
Those are the wavelengths.
So it's further to go from 5 to 2.
Mm-hmm.
Yeah, those are the
Okay.
yeah. So the wavelengths are smaller,
Yeah.
but that means the energy's bigger.
Right.
It's
I thought
inversely.
you said the opposite.
No.
That confused me. Okay.
No. The smaller the wavelength, the greater
Greater,
the energy. Okay? That's why you got to have those three things lined up in your mind: wavelength, frequency, and energy. Okay? Okay, here's a question. All right? Now, I want to calculate the wavelength of light emitted when the hydrogen electron transitions from 6 to 5, okay? So it's going from 6 to 5. So the equation that we need to do this is which one?
The one with the Bohr's constant.
Yeah, the one with the Bohr's constant, okay? And so the Bohr's constant is coming from what? It's coming from H times C times R sub H, okay? So that's where that number is coming from, okay? And this is written out as if you were to just plug one n value into here and solve for it. But the equation I gave you is better because it shows you final minus initial. 1 over n 2 squared minus 1 over n 1 squared, and it shows it in that manner. Okay, so this is what we're going to do. We're going to first find the energy. Once we find the energy, we're going to find the energy that's associated with that photon, and then we're going to solve for that energy using the equation that we talked about at the beginning of class. That is that you can solve for energy if you know the wavelength, okay? Or you can solve for the wavelength if you know the energy of that particular transition. So we're going to find E first, and then we're going to solve for lambda, okay? So here is the calculation that we're going to do, okay? Now, if you use the equation that I gave you, okay, you'll notice that these two numbers are flipped, okay, and that negative number goes away, okay? You end up getting the same value regardless, okay? So if you multiply that out, that's going to be 1 over 5 squared minus 1 over 6 squared, so that's 1 over 25 minus 1 over 36. I would do that in the calculator first, then multiply it by that number, okay? And when you take the negative of that, you end up getting this number over here. Now that's the change in the energy in the atom. That's the energy that you're going to observe, and you'll notice that it's written out as a release of energy, okay? Now, what you want to do when you're going to try to solve for the wavelength of a particular light is you want to take that number and you want to take the negative of it, okay? This is kind of like when you're looking at the system versus the surroundings, like what we were doing with the calorimetry question. Here you need to take the negative of that energy value because you're not going to get a negative wavelength. That doesn't make any sense, okay? So whatever number that you end up calculating for the energy that's released, take the absolute value of that number before you move on to the next step, okay? That's a good way to think about it. Once you have the energy associated with that transition, then you can solve for the wavelength, okay? You would use this equation. Lambda is equal to Planck's constant times the speed of light divided by the energy. So here's Planck's constant, here's the speed of light, and then there's the energy we just calculated for the equation above, okay? It looks bad, but really what is this? This is multiplication and addition when it all is said and done, okay? That's what we're essentially doing here. What happens to the units? Joules cancel, seconds cancel, and you're going to be left with something in meters. Okay? Say something. Is this exhale? Okay? Does this make sense?
Yeah.
Right?
It's just a lot of
It's
information.
a lot of information, okay? I know I'm hitting you hard with this PowerPoint. This is why I don't like PowerPoints, because I can put tons of information on PowerPoints, okay? But you've got to go home and do problems about this weekend and make for sure that this makes sense to you, that you can use these three equations that I've been talking about.
I guess what's confusing to me is like, how do you know when to use what equation? And I know it's a very broad
Anytime
question,
you
but
have
it's just,
the, okay, so anytime you have the ends, got to use the Bohr.
okay,
That's it, okay?
and then the other two.
The other two is if, okay, so the other two is if you need to know, so equations that don't have the n values, if you want to say it like that, like if you need to know, okay, I have a wavelength and I want to solve for a frequency. So you gotta know what those two things mean.
Right.
Okay, so that's when you'd use that, is when you're just asking about wavelength and frequency. You bring energy to the party, well then you've got to use this equation. Okay?
Okay. That makes
And if you bring the ends to the party, you got to use that equation over there.
Okay.
And I'd rather you not learn that constant and just recognize that it's just h times the Rydberg constant times the speed of light times the 1 over n1 squared minus 1 over n2 squared. I mean, that's just a lot easier to do, okay, than to have to try to memorize 4 different numbers, okay? Those will all be given to you. I think what makes this weird is that now you've got these Greek symbols thrown in here also, but really, what is it we're solving for? We're either solving for energy, wavelength, or frequency, for all 3 of those.
So I'm confused. If it's N1 and then N2, why is it flipped?
See the negative? See, there's a negative that they put at the front of their formula. Don't let that trip you up, okay? Regardless of whether there's a negative here or not, so you see this is their N2 and this is their N1, but there's a negative in the front. I don't have a negative on this one. Like what would happen if I multiplied that by negative? If I factored a negative out of this, those would reverse.
Okay.
Are you talking about the negative E photon?
Yeah, they're talking.
Yeah.
She's talking about why is there
A negative.
why is
it,
there a
like,
negative at the
switch?
front?
Constant instead of
Yeah.
there.
That's because I don't like to put negatives in the front of my formulas. I just like to say, oh, 1 over n1 squared minus 1 over n2
Is that why they
squared.
flipped it?
Yeah.
Okay.
Now, does it matter either way?
I guess not.
No.
No, it doesn't. Because what are you going to do in the next step? Are you going to have a negative number in the next step?
No.
No.
Because
No.
you multiply the two.
Does everybody see why you don't want to have a negative number when you're solving for wavelength?
Wavelength
Because
can't be
that's what
negative.
You don't want a negative wavelength. Like, what's a negative length?
It's like,
Negative 5 meters long.
Doesn't make
it's not.
Okay, so
Yeah.
that's what I'm saying. So even if you screwed that up royally, forgot the negative and everything, you should get a positive number at the end. The only thing you have to make for sure you do is square the n values in the denominator.
Okay.
So, okay, so where did we get the H and the C values? Are those just constants?
Yeah,
Okay.
this is Planck's constant, and that's the speed of light.
Okay.
So when I give you the test, I'm going to tell you what H is, I'm going to tell you what C is, and I'm going to tell you what R sub H is. You're going to get all 3 of those.
Multiply the
And you'll get these equations also, but you got to know when to use them, just like what you asked.
Yeah, that's why I get
Okay,
confusing.
when do you need to use these? You need to use n when you got n, you got to use this equation. Okay? If you've got just wavelength and frequency, you got to use this equation on top.
So there's never gonna be a question where it's referring to wavelength and then energy is given, or energy is.
Sure, you can solve for one or the other. I mean, you could rewrite this equation in the middle and say, okay, well, what is frequency?
Okay.
Frequency is just the speed of light divided by wavelength. So
Yeah.
sure, you could be given a question. Because you should know the relationship between all 3 of those things. N is just the 4th thing coming to the table, okay? Like, what is the distances between the orbitals telling me about the energy? Okay? This is where I was talking about that faith, okay? Like, it's going to make sense, but really right now it's just knowing how to use those 3 equations right there on the board, okay? All right, now I know that this makes everybody want to throw up when they do this problem right here, okay? So, the next question is going to deal with the conceptual aspect of this, okay? Which is, what I said a moment ago, is that if you are transitioning, okay, further away, there's going to be more energy released, correct? And that means the wavelength is going to be smaller than if you have a transition that's closer together. You're going to have a larger wavelength because it's going to have less energy associated with it. So that's what you've got to remember. The bigger the wavelength, the lower the energy. Okay? Now, what I would like us to be able to do is to solve a question like this. Based on the illustration on the board in class, answer the following questions about the Bohr atom. Rank the absorptions by wavelength, smallest to largest. Rank the emissions by increasing energy, smallest to largest. And which emissions, if any, are visible. Okay? So this is something you need to write down. Okay, so here's a Bohr atom. We got a nucleus. All right. We're going to have some shell 1, 2, 3, 4. Okay. So I'm going to have a transition that's going to go, let's say, from here to here. We'll call that A. I'm going to have a transition here from here to here. We'll call that B. I have a transition, let's say, here from here to here. I'll call that C. I'll have a transition here to here. We'll call that D. I'll have a transition here to here. We'll call that E. And we'll have a transition here to here. We'll call that F. Now, I know I haven't spaced it evenly. I know this is not to scale. I know that picture shows what a terrible artist I am, okay? But I think everybody can recognize that some arrows are going towards the nucleus and some arrows are going away from the nucleus. Everybody see that? Say something.
Yes.
No, you see that, okay. So what do I mean by an absorption?
It's taking in
It's
energy.
taking in energy. So if you're absorbing energy, are you going towards the nucleus or away from the nucleus?
Towards it.
You're going away from the nucleus because you're absorbing energy so you can go further away. So if you get energy, you start to go further away from the nucleus. You're absorbing energy. Okay? So as you go away from the nucleus, you're absorbing energy. So draw a little picture like this. Nucleus, going away from it, absorption. Okay, so you're absorbing energy. So what would happen if you were going towards the nucleus? You're releasing energy. So that is a emission. That's when you see the color, is when the light, when the electron goes down, it releases an energy. So that's an emission. It's emitting a photon. Does everybody understand that?
Backwards in my head, but I guess.
So an absorption is like an endothermic process, like it as absorbing energy. Okay? So it's going up the ladder, so to speak. Okay? Then if it's emitting energy, well, that's an exothermic process.
That makes more sense.
Okay? All right, so who are my absorptions? So my absorptions are A,
C.
C,
E.
and E. Everybody see that? A, C, and E? Okay, what about my emissions?
EDF.
B, D, and F. Okay, and now I've got them, I know who's who, all right? Now, the first question is to rank the absorptions, that's the stuff on the top, those three, A, C, and E. Rank the absorptions by wavelength, okay? That means I want to go from smallest wavelength to largest wavelength. Like that. Okay. So you've got a transition here is going from 1 to 2. This one's going from 2 to 3. And this one is going from 3 to 4. Okay. So which one of those would have the most energy associated with it?
Okay, those have the most energy.
Isn't the greatest distance between
Right. So between 1 and 2 is the greatest distance, okay, right?
Mm-hmm.
And if you forget that, just do that math in your head real fast. 1 over 1 squared minus 1 over 2 squared is 3/4. You're comparing that to 1 over 2 squared minus 1 over 3 squared, which is
Smaller.
much smaller. And even this one, 1 over 2 squared minus 1 over 4 squared, is still much smaller than 3/4, okay? So the one that has your greatest energy is going to be A. So which one will have your smallest wavelength? A. Smallest wavelength, largest energy. Okay, so which one would have your largest wavelength?
E.
It would be C, because you're transitioning from 2 to 3 versus 2 to 4, okay? So since you're both starting at the same place, here you're only going to 3, here you're going out to 4. So that means that the one that should have the largest wavelength and should be the smallest energy should be C. And the one in the middle will be E. Does that make sense? So I feel like everything came off the rails there when I said that A had the smallest wavelength and the largest energy. Why is that?
Because I guess, like, for me, like, I'm thinking everything backwards, I guess, in my head, like, because I just think, the more energy, like the further the distance, the more energy there's going to be, and the lower the wavelengths.
Yes.
And then I think so I don't know.
Well,
I see that.
no, I mean, what I'm saying here is that, do you agree that the distance between 1 and 2 is greater than the distance between 2 and 3, and 3 and 4, and 4 and 5?
Yes, and I guess also the way that it was drawn, I forget
Yeah,
that.
don't look,
the
yeah, that's
three-
not to scale.
The 3 and the 4 is not
It's
to
not to scale, okay, so that's
So-
another thing, is I did not draw it to scale, so I expect you to know that the distance between 1 and 2 is greater than the distance between 2 and 3,
Because
and
visually
3
it
and
looks
4.
bigger in other areas, but then, yeah.
Okay, what about the reverse? Okay, like, what about the emissions? The emissions, I want you to rank them from smallest to largest energy.
So the smallest would be D, right?
So you've got 2 to 1, 3 to 1, 3 to 2.
smallest usually don't that much,
Why do you think that?
because it's smaller and 2 to 1 is bigger than 3 to 2.
That's correct. So, in other words, the distance between 3 and 2, okay, is going to be the distance that's actually the one that's the smallest, okay? So that should be the one that has the lowest energy, okay? And both of these are transitioning to the first energy level, and we've already said that the distance between 2 and 1 is really big, okay?
Would it be like FED?
It would be F is the smallest, okay? Which would be the largest?
Then D, or B will be the biggest. B will be the biggest.
B will be the biggest because you're going from 3 to 1, and then D would be 2 to 1, okay? And which one of those emissions would be visible? Do you all agree with that?
I think D because it's the biggest. Like it's
How can you tell which something is visible or not? I gave this to your notes.
It goes to shell 2.
If it ends up at shell 2, which one of those emissions is ending up in shell 2? That's a visible one. Okay, so which emission is ending at shell 2? And it's F, okay? Which ones would be in the IR? Which emissions would be in the IR?
I write this part down apparently.
None of them.
There are none.
Yeah.
Okay? Because I said that in order to be an IR, you'd have to end at like, can't be 1 or can't be 2. You'd have to end at like 3 or 4 or 5. So both B and D are ending at 1, which means what kind of emission are those?
Light or
UV.
visible.
UV. Okay? Faith. Okay? So this is something you've got to conceptually think about over the weekend, all right? So the question that I'm going to probably ask on the exam is going to have these two parts where you're going to need to, conceptually how to put that together in emissions and absorptions, and you're going to need to know how to solve for E using that Bohr equation. I'll give you the constants. I don't expect you to memorize those, but you need to know how to use those formulas, okay? This is all talked about in I believe chapter 7 in the textbook, so start looking over that this weekend, okay? We'll get through the rest of this on Tuesday.